Hi everyone, I'm Deepak. I'm a final year PhD student at Stanford, and I'm excited today to talk about our ideas to generalize cluster scheduling policies to be heterogeneity aware. This is joint work with Keshav and Fiodar at Stanford, Amar at Microsoft Research, and my advisor Matei. Machine learning training is an increasingly important and computationally expensive data center workload. To keep up with this growing demand, a number of different specialized accelerators like GPUs, TPUs, FPGAs, and other domain-specific ASICs have been developed. These accelerators are available both in the public cloud, like on Amazon, AWS, and Azure, and also in private cluster deployments for companies and research groups. However, it is not immediately clear how one should actually pick between these different resource types. For example, the goal of a scheduler in a shared on-premise cluster with various jobs and resource types is to allocate resources to these jobs while trying to optimize some global objective. One way of doing this in this heterogeneous regime is to maintain independent subclusters for each resource type and defer choice to the user. Users can decide which resource type they want to use. This is challenging to do in practice, and users might just defer to using the fastest resource type available. This can lead to an ineffective use of resources, since slower resource types will seldom be used. Instead, in this work, we try to show how a scheduler can do better by dynamically allocating heterogeneous resources to a given set of training jobs. Doing this effectively requires addressing two challenges. The first is a challenge of heterogeneous performance. Models and operators today enjoy vastly different performance across the available resource types. Quantitatively, we see that a transformer model, which is used widely in natural language processing applications, experiences only a 3.3x speedup when moving from a K80 to a V100 GPU. However, a ResNet 50 job sees a speedup of 9.6x when moving between the same set of resource types. Giving each of these jobs equal time on a V100 and K80 GPU leads to a vastly worse outcome for the ResNet 50 job. In general, we observe that jobs experience pretty varied speedups across these different resource types, and disregarding this heterogeneity can lead to suboptimal allocations. The second challenge is that different deployments might want to optimize various objectives, and performance heterogeneity needs to be accounted for in different ways based on the objective to be optimized. Objectives can be specified over single jobs, for instance, maximizing the throughput or minimizing the cost of a single job. And such decisions can usually be made fairly easily by just inspecting the throughputs of the given job on the different resource types. There are instances where single job objectives can become harder to optimize. Minimizing costs subject to per job time SLOs might require jobs to be moved from fast but expensive resource types to slow but cheap resource types midway through training. Multi-job objectives make this allocation problem even more challenging. In the extreme case, policies can be hierarchical. An organization might be composed of a product and research team, and resources across these teams might need to be divided using a weighted fairness policy. However, the product and research teams themselves might allocate resources to individual jobs using different policies. For instance, fairness and FIFO. Resources need to be allocated to different jobs while being cognizant of these different constraints. Even though there's a rich line of work of cluster schedulers for deep learning workloads, we see that no previous work actually addresses both of these challenges. Cluster schedulers like Gandiva, Themis, and Tiresias disregard performance heterogeneity completely, while Allocs and Gandiva, even though they do consider performance heterogeneity, they tightly couple their target objective to the scheduling mechanism, making it hard to generalize to other policies. Gavel is our new heterogeneity-aware, preemption-based scheduler that aims to address these challenges. Gavel supports both on-premise and cloud deployments and generalizes a wide range of existing scheduling policies by expressing policies as optimization problems over the allocation. Gavel uses an abstraction we call effective throughput to allow optimization problems to incorporate accelerator and workload heterogeneity, and uses a policy-agnostic round-based scheduling mechanism to ensure that jobs actually receive their computed optimal allocation. Gavel can improve objectives such as average job completion time by as much as 3.5x. Applications in Gavel are written in existing frameworks such as PyTorch and TensorFlow. Gavel requires that either applications provide throughput estimates for how they perform on different resource types, or use Gavel's throughput estimator module to estimate these throughputs on the fly. Given these throughputs, as well as the target objective, Gavel generates allocations for each running job. Allocations in Gavel specify the fraction of time each job should receive on different resource types. And given this allocation, Gavel's scheduling mechanism then actually makes scheduling decisions where it decides what resources each job should receive at any instant in time. For time reasons, I'm going to focus on the policy and scheduling mechanism modules of Gavel. For details on Gavel's API, which specifies the interface between jobs and the scheduler, which facilitates easy preemption, as well as Gavel's throughput estimator, I encourage you to check out our paper. Our goal with Gavel is to make a variety of scheduling policies heterogeneity-aware. These include simple scheduling policies such as FIFO and shortest job first, more complex fairness policies as seen in recent work, and even hierarchical policies such as the one I described earlier. One of our main insights in Gavel is that policy objectives can be expressed as a function of each job's observed throughput, as well as its application. For instance, to minimize makespan, the total time taken to finish a collection of jobs, one can express the duration of each job as the number of training steps divided by the observed throughput. As another example, the least attained service policy tries to give each job equal time on resources regardless of heterogeneity. And this can be thought of as a max-min optimization problem. However, as we noted earlier, jobs can see unequal throughput reductions on heterogeneous clusters. This means that allocations that do not consider performance heterogeneity can lead to suboptimal allocations. To counter this problem, we express allocations in Gavel as the fraction of time a job should spend on each accelerator type. Concretely, an allocation could, for example, specify that job 0 should spend 60% of its time on a V100 GPU and 40% of time on a P100 GPU, while job 1 should spend 20% of time on a V100 GPU and 60% of time on a P100 GPU. Visually, this is what this allocation looks like. Allocations may be recomputed at periodic intervals of time or in response to certain reset events, a new job arriving at the cluster or an old job completing. The optimal allocation depends on the specific objective that we want to optimize. Gavel's other main insight is an abstraction that we call effective throughput. Effective throughput is the time average of individual throughputs jobs observed on each of the resource types and can be computed by a dot product of the raw throughputs, which we represent by T, and the allocation. So T is a matrix of raw throughputs of each job on each resource type. Effective throughput helps us capture the effect of moving a job from a faster to a slower resource type by explicitly considering this matrix of throughputs. Now we observe that the least attained service policy from before in the completely homogeneous setting can be expressed as a max-min optimization problem over the allocation as we defined it in the previous slide. The same policy can also easily be made heterogeneity aware by computing max-min fairness over normalized effective throughputs instead. Note that we need the normalizing factor here to ensure that we can compare throughputs across different jobs. For example, a ResNet 50 job could train at the rate of hundreds of samples per second, while a more computationally intensive language model might only be able to train at the rate of tens of samples per second. And so this normalizing factor allows us to be able to compare these quantities across different jobs. Other policies can be similarly expressed as optimization problems with objectives in terms of the effective throughput. And you can see our paper for details on how we actually do this. Gavel can also support other several common performance optimizations used to better utilize resources in the cluster. Space sharing is an example of such an optimization in which multiple jobs can run on a single GPU in parallel. Here, objectives in terms of the effective throughput would be unchanged, but the allocation matrix would need to be expanded to consider each job combination. We also need to deal with the big question of how to estimate and measure the throughputs of these job combinations. And as we show in our paper, we are actually able to estimate these quite well with minimum overhead. Given these optimal allocations, there's still this big picture question of how to go from these matrices of time fractions to actual scheduling decisions. Concretely, given this matrix of numbers, how should I allocate resources to jobs 0 through 3? And how should they receive time on the 3 GPU types that I have available in my cluster? Gavel solves this problem using a round-based scheduler. Each round is for a prescribed duration of time, and Gavel's scheduler needs to determine which job should receive accelerator time in any given round and on which accelerator type. For the allocation on the previous slide, Gavel would ensure that the job combination of 0 and 1 always receive V100 time, while jobs 2 and 3 alternate between the P100 and K80 GPUs. I want to emphasize that the round duration in Gavel is a configurable parameter. And in our experiments, we found that rounds with a duration of 6 minutes were able to realize optimal allocations fairly accurately. And our paper has a more detailed discussion of this choice. Gavel uses a priority mechanism to determine which job should be active in any round. Priority for each job is the target allocation divided by the number of rounds received for each job since the last time this allocation was computed. For example, let's consider this target allocation, which specifies that jobs 0, 1, and 2 should receive resource time in various ratios. Let's say that each of these jobs had received rounds according to this matrix, rounds received. We can then compute the priorities matrix, which is just the ratio of the allocation and the rounds received matrices. And then jobs can be placed on resources where they have highest priority. The intuition with the priority scores is that they're high if a job receives fewer rounds compared to what it should have received according to its optimal allocation. I want to conclude with some empirical results. We tried to answer a couple of questions in the evaluation section. The first main question is that do Gavel's policies actually improve objective metrics in a heterogeneous cluster? The second is what is the impact of input load on objectives when using Gavel's policies? Can Gavel's policy framework actually support hierarchical policies? And finally, how do Gavel's policies scale with the number of active jobs in the cluster? To answer the first question, we ran experiments on a physical cluster with 48 GPUs, 8 V100 GPUs, 16 P100 GPUs, and 24 K80 GPUs. We evaluated 2 versions of the least attained service policy, one which is heterogeneity-agnostic and another that is heterogeneity-aware. And we ran these experiments on a trace that uses a Poisson arrival process for arrival times, and jobs are continuously added to the cluster through the duration of the trace. We see that Gavel's heterogeneity-aware policy can reduce average job completion time by up to 1.5x. We also ran experiments on another policy that tries to minimize makespan. And we see that Gavel is able to reduce makespan by 20% even when compared to a baseline that uses ad hoc space sharing first proposed in Gandiva. We note that the Gavel policy here, the heterogeneity-aware policy, does not use space sharing. We also implemented a simulator and ran the same traces, and we saw that our results in simulation have high fidelity to the results we saw on the physical cluster, with a small 8% difference in the worst case. We also wanted to study the impact of input load on final policy objectives. And so to do this, we actually ran some experiments on a simulated cluster with 108 GPUs. And we evaluated each policy on multiple traces with different Poisson arrival rates. In this graph, we show multiple points. Along the x-axis, we show the average input arrival rate. And on the y-axis, we show average job completion time for each of those arrival rates. We want to make a couple of key observations from this graph. The first is that Gavel's heterogeneity-aware policies, the orange and green lines, support much higher average input job rate than the heterogeneity-agnostic last policy shown in blue, using the same set of resources. In addition, we see that for a specific input job rate, 5.6 jobs per hour, so for a given trace, Gavel's heterogeneity-aware policies can achieve average job completion times of up to 3.5x better. And if you were to drill a bit deeper for this single trace and looked at the CDF of job completion times for all the jobs we were interested in, we see that the heterogeneity-aware policies also have shorter job completion time tails. And the reason for these improvements is that Gavel is able to be more strategic about figuring out what resource types each job should run on based on its performance profile. Gavel can also support hierarchical policies. And in the experiment here, we're going to show how a multi-level fairness policy works. We're going to use 3 entities, and each entity is going to have 6 jobs. And each of these entities are going to have different weights. So entity 0 is going to have a weight of 1. Entity 1 is going to have a weight of 2. And entity 2 is going to have a weight of 3. And these weights basically control approximately the ratio in which these entities should receive resources. So now we can visualize how the allocations to various jobs changes as jobs are added to the cluster, and these jobs are belonging to different entities. So first we're going to add jobs belonging to entity 0. Now we're going to start adding some jobs from entity 1. And we quickly see that the width of the color bands very quickly converge to the ratios of the weights of these entities. So we can see that entity 1 here has twice the allocation of entity 0. And as we add more jobs from entity 2, the allocations again adapt. And the final allocations for each of these entities are in the ratio of 3:2:1, which is the ratio of their weights as well. Finally, we want to show that Gavel's policies can compute allocations fairly efficiently for a large number of jobs. So here we're showing the runtime of Gavel's policies on the y-axis with respect to a number of jobs on the x-axis. And we see that Gavel can compute allocations for even complicated hierarchical policies within a minute for 2,000 jobs. Computing allocations when the optional space sharing optimization is enabled is more expensive because Gavel needs to reason about the allocations it should give to each job combination, which is obviously more computationally expensive. Besides these questions, we also tried addressing other questions in our paper, namely, how well does Gavel's scheduling mechanism actually realize these optimal allocations? And what's the overhead of preemption in Gavel using its round-based scheduling mechanism? And I encourage you to look at those results in our paper. To conclude, Gavel is a heterogeneity-aware cluster scheduler able to optimize for many higher-level objectives, such as fairness, makespan, and cost. Gavel formulates existing policies as optimization problems and shows how these optimization problems can be made heterogeneity-aware using effective throughput. Gavel is open source on GitHub. Thanks for listening.